Okay, so let's talk about multiplication patterns for moving the place value. So we're going to multiply times values of 10, right? And you've seen these problems many times. They set them up like this. They start like this. Say 4 times 1 is what?
4.
Literally the identity property of multiplication, right? Like one group of 4 has to be 4. Otherwise, multiplication doesn't work and the world ends, right? We're going to represent this in base 10 so that rather than looking at just the digits, you can see the actual value. 1, 2, 3, 4. If we wanted to use base 10 actual blocks, I'll get my magnet blocks out, it would look just like this. Boom, 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 boom. 1, 2, 3, 4. Now, obviously, we don't have room for all the rest of these magnets, so we're going to abbreviate them by using our dots, sticks, and lines. Our next part always looks like this. It's always that increasing by a factor of 10. So we took 10 times 1, or moved our 1 up into the tens place, right? When we do this, what we do is we take each of these 1s and turn those 1 into a 10, or multiply each of the 1 by 10, right? It's our distributive property. 1 times 10 is 10, 1 times 10 is 10, 1 times 10 times 10, 1 times 10 is 10. 10, 20, 30, 40. Correct? How did the value of this 4 change when we went from our times 1 to our times 10? Four plus 0 is 4, though. Tell me more about what you mean by we added a 0. Where did we put that 0 and why did it change the value of the 4? We added a place. We moved that 4 from our 1s place, representing these, to our 10s place, saying, okay, now I've got 4 groups of 1, 2, 3, 4. 4 groups of 10, 20, 30, 40. So we made every 1 worth 10. And this is so not hard so far, right? We're going to start here at our foundation, and then we're going to look at some of the other work we've been doing that's kind of a little iffier. So if I take that 4, and I multiply it times another higher power of 10, this is 10 times 10, right? 1 times 10, 10 times 10. What shape am I going to use to represent 10 of these sticks? Huh? Which base 10 block? What will we call it? A 100 block, just a square, because we don't want to draw the little 100 squares on the inside. If we're trying to do quick picks or shorthand, we just want to say 100, 200, 300, 400. Each one of those represents one of these, so that's 100 in it. 10 times bigger. Now 10 more times bigger, right? 10 groups of 10 is 100. So I took this 10 times 10 is 100. 10 times 10 is 100. 10 times 10 is 100. And 10 times 10 is 100. Or a 4 in the 100th place. Now, how do the zeros compare between the problem and the answer? These zeros, these place value holders. First off, is 1 times 4 ever going to equal anything other than 4? Not if math works, right? Literally identity property. 1 times anything is anything. So when we do this multiplication, could we write it out longhand and do our 1s place times 4, and our 10s place times 4, and our 100s place times 4, and then add them together? Could we do that? Yes, we could. I heard this story. You guys know who Bill Gates is?
Yeah.
He founded a company called Microsoft. This teeny tiny little company that, made computers, a great big deal. Bill Gates, one of the richest guys in the world. I heard this story that he was given an interview, and somebody asked him a question like, if you have a really, really hard job. How do you pick who to give it to? And he said, I'm going to pick the laziest possible person. To which sounds insane.
Yeah.
People on YouTube, everybody's looking at me like this. What? Why? Here's why. He says the laziest possible person wants to keep their job, so they're going to do what I asked them to do, but they're going to find the easiest possible way to do it. Yeah, me too. I was like, that makes a lot of sense. That's why Bill Gates is way richer than the rest of us, because smart dude, right? So, it is not wrong in math class to pick the laziest possible way to do this math that still gets you the right answer. As a bad math student, the first thing I saw was, I got a 4 and 2 zeros, I got a 4 and 2 zeros. I got a 4 and 1 0, I got a 4 and 1 0. I got a 4 and no zeros, I got a 4. I don't have to actually do any math. All I'm doing is moving around numbers. Now, is that doing math? Well, absolutely it is, yeah. It's just doing math efficiently rather than working that out longhand. Is there anything wrong with that? No, absolutely not. If math works, then math works. So let's talk about different ways to represent that. Because we've done those worksheets where we've got these stacks and it looks one way here, and it looks another way here, and it looks another way here. Let's talk about ways to represent this in multiplication. And let's start with, is there another way to represent 4 times 1 as a math problem? Yes, sir.
1 times 4.
Same thing, though. We're talking about a different way to represent this power of 10, a different way to write it.
Word form?
Huh?
Word form?
Word form, yes, but it's harder to solve math problems word form. Word form, we usually, word form is something we need to know so that if we have to write it out, we can. But if we're actually going to solve equations, we want to avoid word form like the plague because you really can't do the algorithm with word form. Can't expand this one, though, can you? It's so simple. 1 is called our base unit for a reason, right? Everything moves out from 1. We've got 1 in the middle, and then we move this way, and we've got tenths, and we move this way, and we've got 10. We've got 1 in the middle, we've got tens, tenths, hundredths. So 1 is so simple, there's not really anything else you can do with it. How about this, though? Four times 10 to the 0 power.
I was going to say that, but I just think.
Exponent form. It looks a little awkward because 1 is so simple to represent anyway. This is actually more complicated than just writing the number 1. But exponent power works, exponent form works really, really well once we start getting into the thousands or 10,000s or 100,000s or millions, where you don't want to write 0, 0, 0, 0, 0, 0, 0, 0. If you don't want to write all those zeros, we can just kind of abbreviate it and put how many zeros does our problem have up here. 4 times 1 equals 4 times a 10 with no zeros on it, which is a 1. And that is 4. That means 4 times 10, or 4 times 10 to the first power. This is how many place values we're going to hold. This exponent number, when we're talking powers of 10, just represents how many place values we're going to hold. Equals 4 groups of 10. And if we step it up one more time, 4 times 100, or 4 times 10 to the second power, 10 times 10, or 10 times 1. Let's put my digits back in here so I can show you a trick. 4, 40, 400. And me, as a poor math student who wanted to take a shortcut, would go, hold the phone, chief. 4 times 1 is always going to be 4 because that's how math works, and the universe kind of ends if that doesn't work. 4 times 10 is 4 to the 10. Wait. This looks like word pyramids to me. Add a letter every time in a word pyramid. 4 times 1, 4 times 10, 4 times 100, 4 times 1,000, 4 times 10,000. Really, all I'm doing is I'm taking that 1 times 4 and then just adding my place values. Is that the lazy way to solve it? Absolutely. And I would totally take it. There are so many things we do in 5th grade math that are difficult and a lot of work and are like 15-step problems and write the equation from this word problem. There are so many things that we do are complicated. Take a vacation on this one and take the lazy way out. Lazy here is very, very effective. All we're doing is taking our digit times our 1 and filling in our place values.